In this video, we're going to discuss the concept of bond enthalpies. So let's start with a couple of definitions. First of all, the enthalpy change is the name given to the amount of heat that is released or absorbed from a chemical reaction or physical change when it is carried out under constant pressure. So some chemical reactions release heat, some absorb heat at constant pressure. And often we carry out these chemical reactions under what are called standard conditions. So when we carry out a reaction under standard conditions, which would be 25 degrees Celsius, 1 atmosphere of pressure, 1 molar concentrations if we're talking about solutions, then if it's carried out under standard conditions, then the standard enthalpy change, which is delta H naught or delta H zero, is the enthalpy change for a chemical or physical reaction carried out under standard conditions. So if we look at this chemical reaction here, the combustion of propane, we see over here we have a delta H value, a standard delta H value. So this reaction releases, because we have a negative sign, 2043 kilojoules under standard conditions. So how are these standard enthalpy changes for a reaction calculated? Well, we can do them experimentally, where you actually perform the experiment and measure it using calorimetry typically. However, this is not always the best option. Sometimes reactions can be difficult, expensive to carry out. So there are also mathematical ways that we can measure standard enthalpy changes or calculate them. We've looked at a few others. The way we want to discuss here to calculate the delta H standard is using bond enthalpies. So what are bond enthalpies, and how can we use bond enthalpies to calculate the standard enthalpy change for a reaction? Well, let's tackle this first question first. What are bond enthalpies? Well, bond enthalpies are defined as the standard enthalpy change for corresponding bond-breaking reactions. So most simply, the strength of a bond is measured by how much energy is required to break that bond, which is the bond enthalpy. So chemical bonds, so we have molecules, and these molecules contain chemical bonds. Each chemical bond has a different amount of energy in it. So the bond enthalpies, and you can see here a whole table full of bond enthalpies. Let's look at one. Here we have a hydrogen-hydrogen bond, and the bond enthalpy is 436.4. What that means is to break a hydrogen-hydrogen bond requires 436.4 kilojoules per mole. If we look at another bond, let's look at a carbon-carbon bond. So if we have a molecule that contains a carbon-carbon bond, it would require about 347 kilojoules to break that bond. You can see a carbon-carbon double bond requires even more energy, and a carbon-carbon triple bond requires even more energy. So we can get a measure of how much energy is contained in a molecule by what types of bonds they have and how much energy it takes to break those. And how much energy it takes to break a chemical bond is what is defined as the bond enthalpy. So a little bit more about enthalpy. And first of all, when we're talking about breaking and forming chemical bonds, there's a few very important rules that we must never forget. First of all, heat is always required when a chemical bond is broken. So in order to break a chemical bond, we have to put energy in, or put heat into it in order to break it. So the enthalpy change for breaking a bond is always going to be positive. So the positive sign means, a positive delta H means that we are absorbing heat in that process. So breaking bonds is what's called an endothermic process because it requires heat. Now, of course, the opposite would be true. Heat is always released when we form a chemical bond. So the enthalpy change for forming a bond would be a negative delta H because we are releasing heat, and therefore the negative sign means heat is flowing out of the system into the surroundings. So forming bonds is always an exothermic process. Now, if it requires, let's say, 436 kilojoules per mole to break a hydrogen-hydrogen bond, then it releases that same amount, 436 kilojoules per mole, when we form that hydrogen-hydrogen bond. So thus, for a chemical reaction, heat is both absorbed and released because in a chemical reaction, we are generally breaking bonds, right? We've got our reactants, and we have to break those bonds, and we have to form new bonds to make our product. So typically, in a chemical reaction, we're doing both. We're breaking and forming bonds. So is the overall reaction endothermic or exothermic? Well, of course, it would depend on how much energy is required to break the bonds and how much energy is released when we form the bonds. So if more energy is absorbed to break those reactant bonds than is released, then that would be a positive delta H for that reaction, and it would be endothermic. And conversely, if more energy is released when we form those product bonds than is absorbed when we break the reactant bonds, then that chemical reaction would be exothermic, and we would have a negative delta H. So for this particular reaction here, our reactants, propane and oxygen, we got to break these bonds, right? There are bonds in this propane, the carbon-carbon-carbon hydrogen bonds, and then our oxygens are bonded together. So this is going to absorb heat to break those. And then, of course, when we form our carbon dioxide and water, we're going to release heat to form these. So as we can see here, we're given the delta H value, and this is exothermic. So what does that tell us? Well, since it's exothermic, we're releasing more heat when we form these than was absorbed when we break these. So let's go back and look at our second question. Now that we've defined bond enthalpies, how can we use these bond enthalpy values to calculate the standard enthalpy change for a chemical reaction? Well, it should be hopefully pretty obvious. To calculate the delta H for a reaction, we take the sum of here we have the sum of D. D is what we use to represent the bond enthalpies. So we take the sum of the bond enthalpies for the bonds broken, right? That would be our reactant bonds, minus the sum of the bond enthalpies for the bonds formed, which would be our product bonds. So basically, to calculate delta H using bond enthalpies, we take the sum of all the bond enthalpies for the reactants and subtract from that the sum of the bond enthalpies for all of our product bonds. So let me give you an example to help illustrate that. It says use the bond enthalpies to calculate the standard enthalpy change for this reaction. So we want to calculate our delta H value standard for this particular reaction here, right? So we've got hydrogen plus chlorine yields 2 HCl. Of course, this is a balanced equation. So what we want to do is not just look at these reactants and products, but we have to look at the kind of the dot structures to see what bonds we have. Now this is a very simple reaction. H2, we have 1 mole of H2, so we have 1 mole of HH bonds, right? Here we have 1 mole of Cl2, so Cl2 is Cl bonded to Cl, so we have 1 mole of Cl bonds. And then we have 2 moles, we form 2 moles of HCl, so H bonded to Cl, so we have 2 moles of those bonds. So we need to figure out the bond enthalpies for my reactants and for the products. And again, we have to take into account that we have 2 moles here. So we look on our chart, our HH bond, right, we've got that. Our HCl, we've got 1 mole of that. Or excuse me, we've got 2 moles of HCl, that's our product. And then down here, we've got our ClCl, so we've got 1 mole of that. So let's write these values down, and then we can plug them in here. So again, our equation is delta H using bond enthalpies, the delta H for this reaction, the sum of the reactant bonds. So remember our reactant bonds, we had the enthalpy for HH bond, 1 mole of that, times the bond enthalpy for the hydrogen-hydrogen bond. We have 1 mole of Cl-Cl bonds, which would be right here, minus the sum of the bond enthalpies of the products. Now we have 2 moles, so we have to take 2 moles times the bond enthalpy for an HCl bond. So again, we got these off our table. And if we perform this calculation, we can see that we have calculated the delta H for this overall entire reaction, and this is negative and exothermic because we're releasing more heat than we are absorbing. Now, here's another reaction. It's a little more involved. I want you to pause the video and see if you can solve the delta H for this reaction using the bond enthalpy method. So remember, draw the dot structures for each of these so we can see how many bonds and what types of bonds we have. Be sure to take into account the coefficients. And then, so pause the video. Let me flip over to the table so you can use that. Okay, pause the video and give it a try. Okay, so the first thing we want to do is kind of draw out a rough electron dot structure for each of our molecules so we can kind of see what types and how many bonds we have of each. So here we have for methane, we have 3 chlorines, so if I count them, I've got Cl-Cl bonds times 3 moles. And then for CHCl3, this is our dot structure. And then HCl, we have 3 moles of those. So it's very important that you draw out your dot structures. If you leave off the lone pairs, that's okay for this. I did it for completion's sake. So to calculate our delta H, we need to figure out all the reactant bonds, the bond enthalpy for each of those, and sum those up. Subtract from it the sum of all the bond enthalpies for my product bonds. And of course, we have to take into account how many moles of each we have. So if I look at each, here for methane, I've got 4 moles of carbon-hydrogen bonds. 1, 2, 3, 4. So 1 mole of methane contains 4 CH bonds. I have 3 moles of Cl-Cl bonds. I have 3 moles of carbon-chlorine bonds. 1, 2, 3. And then I also have 1 mole of carbon-hydrogen bonds. So for every 1 mole of this, how many moles of bonds I have. And then of course I have 3 moles of HCl bonds. So my equation should look like this. I'm going to have 4 moles times the bond enthalpy for 1 mole of carbon hydrogen plus 3 moles times the bond enthalpy for my chlorine-chlorine bonds. And then my products, I've got 3 moles of carbon-chlorine, 1 mole of carbon hydrogen, and 3 moles of hydrogen chlorine. So I need to look on my table and get each of these, the bond enthalpies for each of these. Now again, please be sure when you work these problems to write it out step by step. It's very easy to make a mistake and leave something out if you don't. So I look on my table, which we just had, and I get the the bond enthalpy for 1 mole of each of those bonds and plug them in. Now when I multiply, of course, 4 moles times 414 kilojoules per mole, my moles will cancel. And so I'm going to calculate this for my reactants and my products, the bond enthalpies for my reactants and my products, and I subtract those. And I get a negative value, and to the correct number of sig figs, I get negative 340 kilojoules. So this is an exothermic reaction because we are releasing more heat when we form these bonds than we are absorbing when we break these bonds. So be sure you practice a few more of these bond enthalpy problems so that you get proficient at it.